Okay, so we're still in section 3.1, but we want to talk about second derivatives now. Okay, and so um, I just wanted to take a look to see what will the second derivatives look like in each of our situations here. So we see here that we have a critical number there because the derivative is 0, and then we have a critical number here because the derivative is 0. That may have looked like a sharp point, but I meant to make it look smooth here. Here we have a derivative that is 0. And here we had a derivative that did not exist at this point, right? The derivative jumped from being a positive number to being a negative number, but the function still exists here. Okay, and then over here we had another horizontal, or another critical point. Good. And so the question then is, at each of these critical points, we have 1, 2, 3, 4, 5. Do we have a local max or min? And so we could use the first derivative to check for us, but we could also use the second derivative. So here at this point, notice that the first derivative is 0, but then the second derivative is positive. So at this point, we have f prime, let's call this x1. F prime of x1 is equal to 0, but f double prime of x1 is positive, right? Similarly here, right, our f prime at x2 is equal to 0, and f double prime at x2 is negative. And so this one corresponded to a local max, and this one corresponded to a local min. I need my coffee. That's a local min, right? That's a local minimum, and that's a local maximum. Good. All right. And so here's x3, and of course, once again, we see that f prime of x3 is equal to 0, but then f double prime of x3 is positive because the curve is concave up. And so therefore here we will have a local minimum. Let's see if I can spell that correctly. Okay, here the second derivative is not going to help us here because our first derivative does not exist here. And so here you would have to use the first derivative test. Okay, because again the first derivative does not exist here, but the first derivative does change from positive to negative here. Okay, so that's how I would know that there's a local maximum there. And here we do have both the first and the second derivative that exists here. And again, just like this one, the first derivative is 0, second derivative is positive, and so you end up with a shape like that. Good. And so we have a local min. Good. All right, so what is the second derivative test? Suppose that f prime of p is equal to 0, and so that's automatically excluding this point, right? And we're going to be tricky here. We're going to say I'm going to assume that f double prime of p is not equal to 0. Okay, because that gets us into a different situation. Then if f double prime at p is greater than 0, which happens here and here and here, then a local min occurs at x equals p. Okay. Running off the bottom of the page here. If f double prime of p is negative, then a local max occurs at x equals p. And that's similar to what happened here. We didn't get one there, right? Good. And so this is the second derivatives test. Second derivative test. I don't want to put an S on that. Second derivative test. Good. So I'm going to pause for a moment and set up an example. Let's see, before I do a full example, I just wanted to mention some of the conditions on the second derivative test. We said that f prime of p was equal to 0 and f double prime of p is not equal to 0. Why are we making that restriction? Well, so for example, consider the function f of x just equals x cubed at x equals 0. Right, so our function looks like this here. Good. And so f prime of x is 3x squared and f double prime of x is 6x. Now if I put in x equals 0, I get 0 for the first derivative, and if I put in 0 for the second derivative, I also get 0. So does that mean that if f prime of 0 and f double prime of 0 of x is 0, then I don't have either a local max or min? Well, unfortunately, that's also not the case, because consider the case where we have, this is kind of a flat bottom here. This is f of x equals x to the fourth at x equals 0. And so notice again, f prime of x is 4x cubed, f double prime of x is 12x squared. And so again, both the first and second derivatives are 0, and we have a local minimum there. And the third case, how about if f of x equals minus x to the fourth? Then of course the first derivative and the second derivative, I'll just go ahead and write them down. Minus 12x squared. These are again both 0 at the origin, but of course what do we have at the origin here? A local max. So in all cases, right, no max or min at 0. And then here we had a local min at 0. In fact, it's a global min, but that's okay. And then local max at 0. And in all three of those cases, right, f prime of 0 is equal to 0, f double prime of 0 equals 0, f prime of 0 equals 0, f double prime of 0 equals 0, f prime of 0 equals 0, f double prime of 0 equals 0. Right? And so we were unable to distinguish between these three situations if both of these are equal to 0. And so therefore you need more information. However, notice that in each of these cases, if you had used the first derivatives test, what would have happened? Here the first derivative is positive, and here the first derivative is positive, and so you would have known, right, that this was not a local max or min. Here the first derivative is negative, and then it's positive, which means you do have a local max or min. And then the first derivative test here would have told you that this is a positive versus a negative. And so the first derivatives test actually tells you a lot more information than the second derivative test, but sometimes the second derivative test is a lot easier if the second derivative is not equal to 0. Okay, very good. Okay, now on to an example. Alright, so here's an example where we're given the formula for f of x, the formula for f prime of x, and the formula for f double prime of x. So, the formulas are given to us in nicely factored form, so we can easily determine some of these points. So, in part A, we want to find all the critical points. So we want to find where the f prime of x is either 0 or does not exist. So f prime of x, set it equal to 0, and you see it's equal to 0 where the numerator is equal to 0, so that's going to be x equals 4. And then it's also got a critical point where the denominator is equal to 0. So even that's, although it's x to the 1/3 power, if we set x to the 1/3 equals 0, right, then x is equal to 0. And then finally, 6 minus x to the 2/3 equals 0 means that x is equal to 6. Good. Now you might notice right at these 2 points where the derivative does not exist, the function actually does exist there, right? So at 0, the function is 0, and at 6, the function is 0. So we don't have that problem in that previous example where we had a vertical asymptote. Okay. Now we want to find the inflection points, and remember that an inflection point is where the concavity actually changes in sign. So that does happen where a derivative, the second derivative is 0, but more generally, right, we're just looking for a change in the sign of the second derivative. So where can the second derivative change its sign? Either at x equals 0 or x equals 6. So you could do a little sign chart here for the inflection points, f double prime of x. And then we have a possible inflection point at 0 and a possible inflection point at 6. Good. Now if we plug in a negative number here, a negative number to the 4/3 power, remember that you're going to take that to the 4th power and then take the cube root. So that will be a positive number. Oops, that's a positive number, but oh, that's a positive number too. But then the -8 on the top makes it all negative. I forgot the -8 on the top. Good. And then what happens when you plug in a number between 0 and 6? For example, x equals 1. That's positive. 6 minus 1 is positive, and that's negative, so that's still going to be negative, right? So is x equals 0 a point of inflection? It is not. Okay. And then what happens after 6 here? Let's see. How about x equals 7, for example? If x is equal to 7, that's positive. 7, that's -1 to the 5/3 power. Remember that -1 to the 5th power is -1, and then that would be the cube root of -1, which is negative. But then we have a negative on the top, so negative divided by negative will be positive. Good. So we do have a point of inflection at x equals 6, even though the second derivative is not defined there, right? So x equals 6 is a point of inflection here. The concavity changes from negative to positive. Very good. Okay, next we'll do a sign chart for the derivative. And so what points are going to be on my x-axis? I still have x equals 0 and x equals 6, but I'll also have x equals 4 for the top. And now we want to plug in some test points into our derivative to see if they're positive or negative. So if I plug in a number that's less than 0, a negative number, negative to a cube root is negative. Negative on the top is positive, so far I've got 2 positive numbers. And is that one going to be positive or negative? That one will also be positive, so positive, positive, positive all around. Oh, I should say, did I say that correctly? Maybe I better take a look at this again. If I plug in a negative number, I get a positive on the top. That's going to be negative, and that's positive. So positive, negative, positive, that's going to be negative. Okay. And then a number between 0 and 4, for example, 1, that's positive. 1 to the 1/3 is positive. 6 minus 1 is positive. Positive all around. Good. So we do get a switch at 0, right? Next, between 4 and 6, how about 5? So 4 minus 5, that's going to be a negative number now on the top, but positive and positive on the bottom. So that's negative overall. So at x equals 4, we also have a switch. And then at a number bigger than 6, say 7, that's going to be a negative number now, and that's a negative number, but this negative number is being squared, right? And so that'll give us a positive number down here, positive, negative. So positive, positive, negative means we have a negative, and so no change. Positive, did I say that right? Let's double check. Negative, positive, positive. Good. So that's negative. Good. So we do have 2 switches of sign, right? at 0 and at 4, but not at 6. Good. Excuse me. How about the second derivative test at the critical points? Maybe I can get a cup of coffee. So how about at x equals 0? Well, we can't use the second derivative at test at x equals 0, right? Because our second derivative does not exist at x equals 0. How about at 4? At 4 we could. What's happening at 4? The second derivative is negative at 4. And so therefore, if it's negative, we have concave down, right? And so this is also telling us that we have a max there. Good. We have a min here. And then here at 6 we don't have anything, and I couldn't use the second derivative test for that as either, right? So the only one I could use a second derivative test for was at x equals 4. Then we have f prime of 4 equals 0, and f double prime of 4 is negative. So altogether we had a local max at x equals 4. Good. And finally, you might just check this out on Desmos just to see what the function looks like. If you're curious, I'll stop here.